Okay, 17.3. Can do. Checkpoint 17.3. Right, an inductor of cell inductance, that's an inductor, cell inductance L is connected in series with a switch S, and a battery of EMF V, as shown in the diagram. Sketch a graph.
Hello?
Yeah.
Yeah.
So have you done this one, number one?
Yep.
Okay, let's see whether you got the graph correctly. Sketch the
This is
graph,
checkpoint, right?
how the current in the circuit varies with time after the switch S is closed. This is memory work only, nothing much. Right? Greater inductance, greater resistance to rise of current. So that is where A, right, is exponential actually. And then final current is V over R. On the same axis, on the same graph, get a second graph when the inductor is substituted with another of the same resistance, but twice the self-inductance. Right? Twice the self-inductance, right? Greater L. Okay, it will take longer time. That means it will produce back EMF greater than previously. So it will take greater time to reach the final value. Okay with that? Okay,
Yeah, okay.
Number two, a coil of wire of cell inductance 36 millihenry is connected to a battery. The current takes 60 milliseconds to reach the maximum steady current of 1.5 ampere. What is the mean back EMF? Okay, what formula to use? What formula to use?
This is checkpoint, right, teacher?
Point 3. Checkpoint 17.3. This is to do with cell inductance. What formula?
E equals to negative L di dt.
Usually we won't bother about the negative lah, because we want the positive answer only. Right? Negative is Lenz's law. Remember this formula, put in your value, change it to Henry, and that is your 1.5. That's your millisecond change to second. Okay, good. Hope you have got the answer. Not afford to be careless. Number 3, solenoid is 300 turns. When the current in the solenoid is 1.8 ampere, the magnetic flux linked with the solenoid is given per turn. Calculate the cell inductance of the solenoid. Okay, what should I do? What formula to use?
Li.
Li. Li, how to calculate that?
No, Li equals to 300 times 0.042.
Okay, good. Li equals to the flux linkage. So L is flux linkage over I. Then your I is 1.8. And you are told that got 300 turns. And then this is Weber per turn. 0.42 times 300. Okay, 7 Henry, very high. Okay, a motor connected to 240 volt supply rotates at 500 revolution per minute. The current in the armature has a resistance of 2.5 ohm and current is 2.4 ampere. What is the back EMF? Okay, how do we calculate that? What formula to use?
E back equals to V minus IR.
Okay, this formula V naught or supply voltage is equal to I times R plus E back. So E back is V naught minus IR. Put in your value, 140 volt. And then I is 2.4, R is 2.5, then you get 234 volt. Okay. When the load is applied to the motor, the speed of rotation becomes 200 revolutions per minute. Remember this per minute. Calculate the back EMF. Okay, this is also 2 per minute. So you just use your I naught sine omega t. Back EMF is just your L di dt. So differentiate that. Okay. If you don't know the formula, the back EMF is proportional to epsilon naught. You now use that straight away rather than go and differentiate it to get this formula. And know that the amplitude of the EMF is proportional to your frequency. So the EMF 2 over omega 2 equals to the EMF 1 over omega 1. Then you want back EMF take omega 2 across there. Okay. Omega 2 is 200. Omega 1 is 500. That EMF initially that we have got initially is 234. Here, calculated. The new armature current, see, just using the formula, that's all. Armature current now, your new back EMF, that one, and then that is your still the same. This one doesn't change. Okay, you can take your EP across that, then divide by R. Remember, EB is this one. Put in your value, calculate out. Okay, how to calculate the mechanical power produced? Yeah, how to calculate? Mechanical power produced. What formula to use?
IE.
I times EB. I times EB. Put in your value. Your I, your EB. And calculate out. Okay. Any comment?
Okay.
If not,
No.
as good. Let's carry on. Number 5. A motor is connected to a voltage supply. When the motor is not loaded, it rotates freely. When the motor is loaded, its speed of rotation decreases and the armature current increases. Explain why. Okay, how to explain? When the motor is loaded, the speed of rotation decreases and the armature current increases. Explain why.
When motor rotates freely, E is directly proportional to frequency of rotation. F is large.
Okay. Then what happened?
armature current is small.
When the speed rotation decreases, what will happen? Yeah, what will happen if the speed decreases? Yeah, right. AMF proportional frequency or omega, right? Frequency is large, then you got large back EMF. So when the frequency decreases, sorry, motor is loaded. When the motor is loaded, the speed of rotation decreases and the armature current increases. Okay, so when the speed decreases, why large frequency? With large frequency, the back EMF is going to be small. As the speed slows down, right? This is the case initially for high frequency. Then the BMF is going to be large, but now the speed slows down. Right? Remember, the speed slows down, the back EMF will decrease. If the back EMF decrease, then it shall be not. V0 stays the same, R stays the same. So it means that voltage supply is constant, armature current will increase. Hence, explain the consequence if the armature or the motor is prevented from rotating. Yep. What happens if your frequency is 0? That means you overload the armature or overload the motor. Can? When armature is prevented from rotating, the frequency is 0. The back EMF is 0 also. Back depend on frequency. Current in the circuit is just V divided by R. That means it's very high. High, it will damage the coil or armature. Okay with that? Anything not clear?
Yeah, yeah.
Okay, okay, let's go to 17.4. Current in the inductor of cell inductance 90 millihenry is 0.5 ampere. Calculate the energy stored in the inductor. What is the form of energy stored in the inductor? Okay, what formula to use? Yep. You should have done the whole homework. What formula to use?
1 minute, I think.
Yeah, U equals to Li square. Put in your value. Half.
Wait, which question is this, teacher?
Number 1.
Number 1.
Number 1, 17.4.
Oh, I thought
Yeah, that's all.
something else.
Finding energy, memorize the formula, put in your value, convert it to SI unit. Then remember to square the current and get your answer. So what is the form of energy stored in the inductor? Yep. What's the form of energy? Didn't do your homework.
No, I did. I'm trying to find the
Right? You
answer.
tell me straight away energy stored in magnetic field.
Yeah, 102 Li square.
Okay.
Okay.
Let's go to question 2. When the current in the inductor increases from 2.0 to 2.5 ampere in 5 milliseconds, the back EMF is 0.575 volt. What is the cell inductance of the inductor? What formula to use? What formula to use?
E equals to negative L di dt.
Okay. And then from there, you can get your L. Don't bother about negative sign. Right? Take the di dt down. And your EMF is given 0.7 volt. And then that is your change current. Di dt. 2.5 divided by change it to second. Use calculator. Energy stored in the inductor when the current is 2.5 ampere. Same formula. U is half Li square. Okay. Any comment? Any question? Anything?
No.
This is straightforward. Just to get it to memorize the formula. Okay. If you do it, you should be able to memorize the formula. Let's go to the last one. Mutual inductance. Right, 17.5. When the current in the coil is reduced from 7 ampere to 0, that's the time 0.3 seconds, and EMF of 2.4 volt is induced in the nearby coil. What is the value of the mutual inductance between the two coils? Okay. What formula to use? Yep. What formula to use? Didn't do your homework.
Sorry, what is that?
What formula to use? Should be able to tell me the formula to use straight away, Eddie.
M equals to negative E dl dt.
Then calculate. Yeah, your M, E, don't bother a negative sign there because we want a positive answer. The IDT can take it down and put in your value.
But even you put negative also don't care, right?
No need to put your final answer negative lah. Because it's a positive value, what's the point of putting negative? Right? E is 2.4 and current is from 7 to 0, and then there is your time. Put it inside there, calculate out. That's all. Continue to play with the formula. Okay. Okay, now a bit harder. P and Q are two coaxial coils. When the current in coil P increases from 0 to 2 ampere in 0.5 seconds, the EMF induced in the coil is 0.6 volt. Coil Q then becomes the primary coil, and P the secondary coil. Interchange that. What will be the induced EMF in P when the current of 5 ampere in the coil drops to 0 in 0.2 seconds? Okay. How do I calculate all this? What formula to use? Yes. What formula to use? Didn't do homework.
No, I did, teacher.
Then you should be able to tell me straight away what formula to use.
The formula, V equals to negative M dt
Have a
also.
picture of what you are doing, right? So that you know primary coil, secondary coil, and P and S. Right? Have a rough picture. No need to draw, doesn't matter, but picture in your mind. Yeah, use the formula correct. No need to worry about negative sign there. Right? Calculate your mutual inductance first. Put in your value for the first part. E is 0.6. I is 2. And then there is your time. Okay. So it doesn't matter. M is still the same. Mutual inductance is the same. Use the formula again. That's all. M is 0.5, 0.15 Henry. The current changes from 5 to 0. And then that is your time. Sorry, change from 5 to 0, correct? And that's your time. Put it inside there, calculate out. Okay, anything that is not clear? Just a bit harder, that's all. Play around with the formula.
Okay.
Okay, let's go to number 3. A search coil, there's a search coil. Is placed at the open end of a solenoid. There's a solenoid, there's a search coil carrying a sinusoidal current as shown in diagram. Using the same time axis, sketch the graph to show the variation with time for magnetic flux linked with the search coil. Right, should be able to get all that. Right, remember that's how you calculate your flux linkage, and then your B is proportional to I current, and then your induced EMF is mutual inductance dI/dt, and then your omega in this case is 5. Then you can calculate your period for the waveform, and then you can draw. Okay, since they have given you the value, then you should put your period there. That's 1.3 here. The time. Then you differentiate. Right. This is a sine graph. Differentiate become a cos graph. Cos graph. Right? Draw on the same graph. Right? Don't separate it. Draw on the same graph. The amplitude may be different, doesn't matter. But the timing must be the same. They want to compare. Okay with that? If okay, let's go to your focus on STPM. Okay. Anything to
Okay.
ask? Okay.
No.
Okay, let's try your structure question. This one. Number 3. Got a question? Identical bar magnet, these two are the same, are released from rest and falls through 1, that is your copper tube, 2 plastic tube of the same dimension. Which magnet will be the first to emerge from the tube? Explain your answer. Okay. Explain to me. Which one will come out first? In which tube will the magnet leave the tube first? Then explain why.
The copper one.
Why copper one?
Because it's metallic.
What has metallic to do with being faster? Remember, this section is, we are interested in induced EMF, electromagnetic induction. Nothing to do with what has to do with metallic. Yeah. It will come out in copper first. Right? Magnet in plastic tube emerge first. Why? Because as the magnet move in, the flux across the copper tube is going to change. Then it's going to produce a back EMF to oppose the motion. Right? In copper tube, as the magnet falls, the changing flux on the tube causes an induced current to flow, producing a force to oppose the motion. Right? So it opposes the motion, it will decelerate the motion. Okay, that's the reason. Cannot, anything not clear? Basic idea is the speed is going to increase, the flux is going to change. So there's going to be induced current in the copper tube. The induced current will flow in such a way as to produce a force opposing the magnet falling down. So it will decelerate the magnet. Can?
Can.
Have we done this one? I think we haven't. Okay, a circular coil of copper wire with entrance, each of area A rotated at constant angular velocity omega about an axis which is perpendicular to the magnetic field B. That's your B. That's your axis. That's your circular coil. Right? You are told about an axis that is perpendicular to the uniform field. Initially, the plane of the coil parallel to the magnetic field, so it's flat, horizontal. The diagram shows the position of the coil at time t. Right? So it has rotated that way. Right? That's the axis of rotation. Write down the expression for magnetic flux linked with the coil. Okay, what is the formula? What is the formula? Can? Didn't do your homework. BAN,
This part only didn't do.
BAN sine omega t.
Oh my God, teacher.
It's from 0. So it's a sine
So you
curve.
know what happened today?
What happened?
It just came out 1 minute ago, 20,000 cases.
Yesterday it was so high. They already warned you already.
No, yesterday was 20,596. Today is 20,889.
Yeah.
Like increase.
Don't be distracted. Concentrate on your tuition.
Oh yeah, sorry.
Don't be distracted. The director already told you already. The next few days will be high already because they increase the amount of testing. So best to stay at home if you don't have to go out.
Okay.
Don't go to crowded places. Deduce the expression for EMF induced in the coil. Sketch a graph to show the variation of EMF with time. Okay, how to get the deduce the expression of EMF? Use the formula, that formula. Faraday's law. Then differentiate this one. Right? Differentiate BAN the same. Sine omega becomes cos omega. Differentiate omega becomes omega. Then sketch the graph. Okay, we have to upgrade soon. Okay. Draw the graph. There's the graph. Right? Remember where is the period? I think there's something wrong here. This is half the period there. Period is here. Sorry. Period. Okay. Right. That is your Okay, that's half the period. That's a period. Huh? EMF is a negative. So it's a cost graph. Cost graph. There's your period there. So your two period will be here. Sorry, two period is so wrong. Yeah. What am I doing? Two period is here. 3 over 2 period is okay. Using computer to draw is not easy, so I have to get it from the internet. That's how the graph should look like. Okay. Then your on the same axis above, sketch the another graph variation. This is the second one, B, C. Sorry. This is your B. Sketch another graph to show the variation of induced EMF with time where the speed of the rotation of the coil is double. Right? Amplitude will double. Right? That one will be 2 times. That one will be 2 times. Okay. So it means that the shape is still the same, except that the amplitude is double. Your period, that's your half period. Half period will be the period for the new one. That's the period for this one. Okay. Can draw the rest. Any comment?
No.
Before the answer, I think your answer is better draw it better. But roughly, that's how it should be. Right? Graph is still the same, except that this is half the period with the period for the red one. Okay.
Okay.
Comment? Anything not clear?
Okay.
Okay. How much time do we still have? Oh, we still got time. Might as well try number 5. Have we done this before? Two solenoid P and Q are arranged coaxially as shown in the diagram. Yeah. Good to draw for you the diagram. The solenoid have the same number of turns, N, and cross-sectional area A. Derive the expression for the mutual inductance of the two in terms of N, A, and length L of the solenoid P. Okay. If the current flowing in the primary is a P, the magnetic field linking the secondary. Okay, that's your solenoid formula. Right? Replace a small n number per unit length with n divided by L. L is the length of a solenoid. Flux in the secondary, BAN. Right? That's your B. Not NI times your AN. Then compare with your flux linkage is M times I. Right? Take the I off, so you got your answer. Okay. From here, just remove the I. We have derived that in class. What is the effect of mutual inductance when the solenoid P is filled with iron core, iron rod? Okay, what is going to happen? Yep, what's going to happen to M if you use an iron rod? Yep. Yep. What's going to happen? cannot remember what we have learned. Right? Basically, we just change this one times this one times your mu r. Right? So we increase your mutual inductance. Okay. Relative permittivity mu r for the iron is very large, so the mutual inductance is increased. Okay. I think we take 5 minutes break, then we'll carry on.
Okay.
Yep. Any question to ask before I stop?
No.
Okay. Take 5 minutes break and try the rest of the question, the essay question.
All right.
Okay, I will stop there. See you in 5 minutes time.